Okay, so we said that we can use mode of operations to avoid problems when we have more than one blocks to encrypt. So here are some basic notation. Let's say that n is the total number of plaintext blocks that we are going to encrypt. K is the key. Mi represent the ith plaintext block. Ci represent the ith ciphertext block. Enc is the abbreviation for encryption, and dec is the abbreviation for decryption algorithm. IV in some of mode of operations, a predetermined value is used, and this is called initialization vector IV. We will see why we need it in a minute. And there are two different actual values, nonce and initialization vectors, and sometimes they are used in an identical way, but actually there are some differences. So initialization vector IV is an input to a cryptographic primitive like block ciphers, hash functions, message authentication codes, etc. And cryptographic nonce, also an arbitrary number, but a nonce can only be used once. Okay, you cannot use the same nonce twice. Nonces and IVs should be generated randomly, so that nobody puts a backdoor to anything. Okay, we will see some examples in a minute. So NIST mode of operations are explained in the document. In the 2001 version of this document, NIST 800-38A suggests the following mode of operations. As you can see, ECB is here, but NIST doesn't say that it is secure. It just shows that there's such a mode, but suggests that you can use the others like cipher blockchaining, cipher feedback, output feedback, or counter mode. Later on, in another document in 2010, they added XTS mode because this is full disk encryption standard of IEEE and other standards, so NIST also added to their documents. So question is, which mode should I choose? And the answer to this question depends on the security and performance needs, okay? Let's see one by one how they work. So recall that we talk about ECB mode. In this mode, every plaintext is encrypted independently, every plaintext block. So you have the ith block, you encrypt it with your secret key and obtain the cith block. Similarly, decryption is just decrypting cith block with the secret key K. So if you want to show it in a picture, you encrypt every plaintext block independently with the secret key. So the person who decrypts it receives the ciphertext, but this time decrypts them back, okay? So here I'm showing the encryption and decryption in different colors because in a few mode of operations later, you will see that the person who wants to decrypt will still use the encryption algorithm here because some mode of operations turns the block cipher into a stream cipher. There you're only XORing the key stream, so encryption and decryption becomes identical. So in a few mode of operations later, you will see that there won't be these dec operations, decryption, but instead it will be enc2. This is why you don't need to always implement the decryption if you are using a mode of operation like counter mode of operation. Okay, so let's look at the advantages of ECB. It is parallelizable. A block can be encrypted without waiting the encryption of other blocks. Random access, a block can be decrypted without waiting the decryption of other blocks. Error propagation is limited to a block. If a single bit of a block is flipped due to a transmission error, it does not affect other blocks. So it has fantastic advantages, but we said that we cannot use it because identical plaintext blocks are encrypted to identical ciphertext blocks, which breaks the security completely. No self-synchronization. If some ciphertext bits are dropped, this synchronization cannot be achieved, right? Because there's no way to understand that, which bits are dropped. So I'm mentioning this because none of the mode of operations I'm going to talk about actually provides a self-synchronization. But when we talk about stream ciphers, we will talk about asynchronous and synchronous stream ciphers. Then we will realize that such a property is a nice one. So this disadvantage does not removed in the following mode of operations I'm going to talk about, but we have to solve this problem, right? Identical plaintext block should not go to identical ciphertext block. So easiest thing to solve this problem is to use CBC, cipher block chaining. Before encryption, every plaintext block is XORed with the previous ciphertext block. We XOR the first plaintext block with an IV. Since everything is, XORed with the previous one, the first block does not have anything before that. So you might say that, okay, let's not use an IV. I mean, let me show you the picture. So let's remove this and do this in this way. Actually, you can do it. But if you want to implement in hardware, this part would be different than the other blocks. So you need to implement it in a different way. So for this reason, implementing in this way saves you the space on hardware. But since you don't have a previous block, we use an IV, which is just a value that is specified in the standards, okay? It is not something secret. Everybody knows what the IV is, and it is fixed. Okay? I mean, some software libraries allow you to change the IV, but you don't need to, okay? So the decryption is like this. The person receives the ciphertext blocks, performs decryption, but this time the XOR operations are at the end, right? And actually this has an advantage. Let's look at the advantages. Error propagation is limited to 2 blocks, right? Fixes the security problem of ECB modes. Parallelizable decryption, but not parallelizable encryption. If you look at the decryption, for instance, if you want to decrypt this, you can start decryption, and you need the XOR of this, but you already have this value. So you don't need to wait for the other blocks to be decrypted, okay? So decryption is parallelizable, but the encryption is not, okay? No random access, no easy way to jump ahead to later parts of the encryption process. And there's also a property coming from the birthday paradox. For instance, if 2 ciphertext blocks are identical, then we have the XOR of corresponding message blocks are the XOR of these. And due to birthday paradox, such a case happens when you encrypt square root of 2 to the b blocks. So for this reason, if you encrypt a lot of plain text blocks, at some point you will see some ciphertext that are identical. So if you XOR the previous ciphertext blocks, those will give you the XOR of 2 plain text blocks. Recall that when we talk about historical ciphers, when you have the XOR of 2 plain text, since these plain texts have redundancy, you can capture some parts or all of them, all of these plain text. So this is not something you want. So for this reason, if you encrypt this many blocks, we suggest you to change the secret key and restart everything. Okay. A third mode of operation is cipher feedback. Instead of a plain text block, encryption of an IV and its XOR with the plain text block are considered as the input in this mode. Here's the mathematical definition, but we can look at the picture to see it in a clear way. But here there is a note saying that CFB mode turns the block cipher into a stream cipher. Let's see what this means in the picture. So instead of encrypting the plain text, you are encrypting the IV. Okay, so you obtain an output here. Then XOR this output with your plain text block to obtain the C ciphertext block. Then you are encrypting the ciphertext block, result is XOR with the plain text block, and obtain the second ciphertext block. And you go in this way, okay? So by saying that this turns it into a stream cipher, we actually, if you look at the outputs of here, you are simply XORing it with the plain text block. So you have the plain text here, and you are XORing this plain text with some random looking output from this encryption process, which in stream ciphers we refer to as key stream. So this is just an XOR operation. So for this reason, when the person who has the ciphertext blocks and wants to decrypt this, actually does the same thing, but only thing changes here the places of C0s and P0s, okay? So this is what I meant when I will be using decryption operation in the future in some of mode of operations. So the person who wants to decrypt also needs the encryption of the IV, so the value here, but instead of XORing it with plain text, when decrypting, we will XOR this with C0 to obtain the plain text. This is why only these 2 places changes, okay? So if you use this mode of operation, you don't need to implement the decryption. So if you have AES, only implementing the encryption version of AES would be enough for you. You don't need the inverse of the S-box or the inverse of the matrix and so on. Advantages: error propagation is limited to 2 blocks. Non-parallelizable, a block can be encrypted if the previous blocks are encrypted. No random access, no easy way to jump ahead to later parts of the encryption process, and so on. So as you can see, this is not something we would like. A similar mode of operation is called output feedback. So it is similar to CFB, but the input blocks are the outputs of the encryption, not its XOR with the plain text. So let me show you the picture. So you might say, what is the difference of this one with the previous one? In the previous one, this line was here. Okay. Now it is here. You might say that what is the advantage of doing this? The thing is that without receiving the plain text first, you can actually encrypt this IV and obtain all of these outputs here. And when you receive the plain text, you can simply XOR it and give the ciphertext. So you can have a press start here, as you can see. So here they say this is IV, but if I use always the same IV and same key, these outputs will be always the same, right? So instead of IV, I will prefer to use the word nonce here, because if I go back here, okay, let me go to CBC. This IV is fixed, and everybody is using that, okay? So the word of IV is correct for me. But here, to avoid misunderstanding, I will use nonce instead of IV, because you shouldn't reuse the same IV here. It causes the same problem when you use the same one-time path. Okay. So I would prefer to use the word nonce here, but I'm sticking to people's notation, because then they will use IV reuse attacks and so on. Okay. So we talk about output feedback. So decryption is again identical. I'm simply changing the places of PIs and CIs. Okay. So no error propagation. Erroneous bits in the ciphertext only affect the corresponding bits in the plain text. Encryption does not depend on previous ciphertext. So it is a nice one. But even better, we can do something even better and use the counter mode. Okay. And these counters should not be used twice. I will come back to this example, but let me first explain what the counter mode is. So what you do is as follows. You choose a counter, okay, encrypt it with your secret key, then XOR it with your plain text and obtain the ciphertext. Then you increment this counter and encrypt that. You increment it. If you have, in this picture, you have n+1 blocks, so you use n+1 counters, okay? Obtain and you encrypt this and obtain the ciphertext. So the person who wants to decrypt does the same operations. They also XOR these counters. So counter or the nonce here is not a secret value. Okay, the attacker knows it, but they don't know the secret key. So they don't know the outputs of these encryptions. So we simply change the places of P0s and C0s or PIs and CIs. So now, as you can see, there are no lines between these blocks. So everything is parallelizable. You have random access and so on. So this is fantastic. It gives you every advantage you want. Like parallelizable, a block can be encrypted without waiting the encryption of other blocks. Random access, a block can be decrypted without waiting the decryption of other blocks. Error propagation is limited to a block. If a single bit of a block is flipped due to a transmission error, it does not affect other blocks. Encryption does not depend on previous ciphertext. So it has almost every advantage that you want. The problem here is that if you use the same counter to perform two different encryptions, it breaks the security. So let me show an example and what happened. So when the ransomware became famous, there was a CryptoLocker ransomware years ago, and some people made the Turkish version of it. So in a ransomware, what happens is as follows. You are infected with a virus, mostly by clicking a link, a spam email, a phishing email. So if you don't have proper security, that virus infects your computer. And what it does is as follows. It encrypts almost every file on your hard drive. But instead of dealing with every file and folder, it chooses some special folders like your desktop and so on. They encrypt all of your files, and then on your screen, they say that they encrypted all of your files and then ask you to pay some money in Bitcoins to this address, then they will allow you to decrypt your files back. Okay, so this initial version did this AES encryption in counter mode, and they only encrypted the first 2 bytes of every file. Instead of wasting time to encrypt 1 gigabyte, they only encrypt the first 2 megabytes, because if you lose the first 2 megabytes, your file will be corrupted anyway, right? So this is what they did. At that time, they asked for 2 Bitcoins to decrypt your files, but Bitcoins was not that expensive at the time. So it was around 2 Bitcoins were like $600 USD at the time. So a lot of people paid 2 Bitcoins to these people years ago. Think about those people selling them at the highest price, which was around like $65,000. Okay, so this is why forensics in case of Bitcoins to check money laundering and so on is important to see if they obtain this from ransomwares and so on. So most of the time when you pay the money, they try to decrypt it back. Rarely they've also lost the key, so they couldn't decrypt and so on. But if you give them the money, most of the time they do. But what we did was to check how they did it, and we realized that they use the same counter for every file encryption, which we always say that in stream ciphers and here, never use the same nonce twice, okay? But they did this, and they use the same nonce. So what they do is as follows. Think about your PIs as a file on your computer, okay? They have a special counter, nonce here. They perform the encryption, then XOR it with your file and obtain ciphertext logs. And now this is the file you see on your computer, okay? They also do the same thing to another file, but they use the same nonce again. So what you do is as follows. You have an encrypted file on your computer, right? But some of your files, you can have a copy. For instance, in case of this happened, it infected a professor at chemistry department. So I realized that one encrypted file was a PDF file that he published as a paper at Elsevier. So I went to Elsevier, downloaded the plain text, and have the plain text version of the file. Okay, so you have the ciphertext here. I have the plain text here. I XOR them, and I obtain the outputs here. Okay, so I don't know the counters. I don't know the secret key, but I have the key stream here. Since they use the same counter all the time, they encrypted every file with the same key stream here. So now we know the key stream. We took every ciphertext on the computer and XORed with the key stream and obtained the plain text back. This is why you should never use the same nonce twice, okay? So counter should be different. For instance, when you are encrypting a file, assume that you chose all zeros here. Then it becomes 1, 2, 3. So if you want to encrypt another file, you cannot restart from all zeros. So what people do is generally as follows. Think that we are using AES. So the block size is 128 bits, right? What they do is randomly generate 64 bits and call it nonce. Then choose the counter as all 0 and perform the encryption. When they want to do another encryption, they regenerate 64 bits as a new nonce. Since you're randomly generating 64 bits, it will be very rare that you generate the same 64 bits, right? So, but they keep the counter again all zeros, and they do this, so they never use the same counter twice, okay? So all your mobile phones, after some version of Android and iOS, they use full disk encryption and they encrypt your files this way. So question is, which counter they are using here, right? If they are using counter mode of operation. Actually, they are using Galois counter mode of operation, but since they are using a counter here, in order to encrypt and decrypt, you should know the counter, right? But the solution is easy because in your mobile phones, you have a hard drive, right? Where you write the stuff, your storage. So it is divided into blocks. So the block number is actually your counter. So when you're writing a file, where you write it actually determines these counters. Since you cannot write a different file at the same place, since somebody is already there, this way you never use the same counter there. Okay. Okay, so Final one, XTS, and then I will show a few pictures how this works. Okay, so XTS stands for XOR Encrypt XOR Base Tweaked Codebook Mode with Ciphertext Stealing. So fantastic shortened abbreviation for this. But as you can see now, we are talking about ciphertext stealing. So AES with XTS mode is a disk encryption standard since 2007 as IEEE standard. For messages with lengths not divisible by B, the last two blocks are treated specially. That is the idea. So it is like a counter mode of operation, but you also have another encryption here where you also increase this counters by using a Galois mode of multiplication, Galois field operation of multiplication. So I'm only showing the picture. If you're interested, you can look at it in more detail, but it is very similar to counter mode of operation. But again, if the plaintext is not multiple of the block size, you perform ciphertext stealing at the end. This is the whole idea. So NIST added this later to its standards. So again, these are some documents for further read. These are the documents for NIST standards, but I recommend Philip Rogers this documentation. It is publicly available on the internet, and here he checks which mode of operations are secure. So if you go back to pictures, you can see that we are actually playing with lines here. We can do many combinations here, take it and take this and put it here, and so on and so forth. So there are many combinations. So here in this document, Philip Rogers actually considers all of these variations and show which ones are secure and which are not. Some of the secure ones are included in this documentation, but there are more mode of operations if you're interested. So let's go back to our motivation and see what counter mode of operation, why counter mode of operation is good. So this is, by the way, I'm always suggesting to use counter mode of operations, but due to the ransomware problem, people think that the problem was due to counter mode of operation. So in Turkey, I see a lot of people saying that don't use counter mode of operation because it is not secure. But actually it is secure as long as you are not using the same counter twice. Okay, but this is well known because you are turning it into a Steam cipher, and in Steam ciphers you never use the same IV twice. Okay, so there is no problem with counter mode of operation if you are using it correctly, and this is why almost everybody is using it. Okay, so let's look at back to our motivation. We said that if I have a BMP file and encrypt it in the ECB mode, we said that it doesn't look nice, right? We can capture a lot of information. So question is, what happens if I encrypt the same image in the counter mode? And this is what you will see. Okay, full noise, no patterns. This is what an encryption should look like. Similarly, if you look at the picture, this is what we get in ECB mode, and this is what you get in the counter mode. Okay.